the incoming electric field is homogeneous, does not depend on position. Actually, it does, but it does not on the length scale of the molecule. This is the essence of the dipole approximation. So, in the approximation where you can neglect the space dependence of the incoming electric field, the polarizability is the dipole response of a molecule to an incoming electric field. So how would you calculate the dipole? You would take the density response, n prime, and calculate the dipole moment of n prime. The dipole moment of n prime is the integral of r, the dipole operator, times n prime of r. Right? What is n prime of r? N prime of r is the convolution of the susceptibility chi times the incoming perturbation. The incoming perturbation is a homogeneous electric field that is described by, again, the R operator. So in this case, the operator that describes the perturbation is the position operator that describes a homogeneous electric field, and this is the same as the operator that you want to measure, that is the dipole. So the polarizability is the integral of R, the position operator, times n prime of R. But n prime of R is the convolution of chi and of R and R prime times R prime, and so this is the formula for the polarizability. Once you know the general density susceptibility chi as a function of R and R prime, you bracket R and R prime with R on the left, R prime on the right. You integrate with respect to R and R prime, and you get a frequency, a function of omega that is the dynamical susceptibility. How to calculate the chi? We saw before. We have this equation that we stated one slide ago that relates chi to chi naught. This kappa kernel is the electron-electron interaction plus the exchange correlation kernel. And by this solution, this equation, that is a linear equation for chi, can be solved formally in the following way. Basically, chi is equal to chi naught multiplied on the left by the inverse of 1 minus chi naught kappa. So basically, the way to go is to calculate chi naught, which can be calculated from ground state ingredients. You do a Kohn-Sham calculation for the ground state. This gives you valence and conduction energies and orbitals. You calculate all these horrible sums over pairs of conduction and valence states. You do this for any pair of positions R and R prime, and for any frequency. A lot of work, but this can be done rather straightforwardly. Then you have kappa. Kappa is also something that you can calculate explicitly. You fill matrices. These chi naught and kappa are big matrices in real space as a function of R and R prime, or if you want, you may transform them into matrices in reciprocal space, G and G prime. You manipulate the matrices, and you get the chi of R, R prime, and omega. You finally integrate with respect to R and R prime. It's a lot of work, but at the end of the day, you get the polarization. Yes?
In the ground state calculation, we use the Bonacon hybrid approximation.
So,
is valid for these excitation states?
Well, it depends on the frequency of the excitation. If the excitation frequency is much larger than the typical nuclear vibration frequencies, you're okay. If you perturb the system with a field whose time dependence has frequencies comparable to the vibrational frequencies, this will not apply.
What is the typical frequencies then?
Electronic excitations are of the order of a volt, a fraction of a volt, or a few volts. So that they are around visible. So from a fraction of a volt to 10 volts. Then you have your UV, then you have ultraviolet excitations, whereas vibrational frequencies are of the order of millivolts or tens of millivolts. So this is a well-established procedure that is implemented in several computer codes. This procedure has a number of drawbacks that we may want to avoid. First of all of many unoccupied molecular orbitals need to be calculated, so this sum over empty states need the knowledge of those empty states. You have to calculate them and to sum all of them. In modern electronic structure methods, you don't want to calculate empty states in general. You want to concentrate on the valence states, and this is something that you don't want to do. You have to calculate, store, and manipulate very big matrices, this K0, kappa. They have to be calculated element by element. And you have to do very complicated matrix operations. And worst of all, you see, you want to calculate alpha of omega. And in order to calculate alpha of omega, you calculate all of these incredible operators, all the excited states, and then big matrices. You multiply, you invert them. At the end of the day, you integrate with respect to R and R prime. You throw all you have calculated away, and you remain with just a miserable function of omega in your hands. So it's a lot of waste. It's a lot of waste. A better approach, then I will make a short. I am always longer than I would like to be. So I present one other slide. We make a coffee break. Forgive me, as usual, a bit shorter than scheduled. Then I will resume for another 20 minutes, 15 to 20 minutes after the break, and then I will give the stage to Paolo, who will tell you about GW. So a better possibility is to solve the Schrödinger equation, the time-dependent Schrödinger equation, in the time domain directly. So remember the susceptibility is the response at time t that would follow a perturbation at a prior time t prime. So one possibility is to perturb the system instantaneously. You introduce a time-dependent spike in the system as a function of time. You have a perturbation at t equal to 0. You follow the time evolution of your Kohn-Sham system as a function of time following that instantaneous perturbation corresponding to initial condition where all the molecular orbitals are in the ground state, and then you calculate the time-dependent dipole. The response, the Fourier transform of the time-dependent dipole thus calculated gives you the susceptibility. Of course, in general, you would do this Fourier transform numerically, and by the Nyquist theorem that we saw the first day, you see that by doing so, you have access to a range of frequencies whose minimum value, the minimum frequency that is accessible to this technique is basically the inverse of the propagation time. So the longer the propagation time, the smaller is the minimum frequency that you can access, and the maximum frequency that is accessible by this, because of the Nyquist-Shannon theorem, is of the order of 2 pi over the sampling rate. So if you sample the susceptibility at intervals of delta t, you will have a maximum frequency of order of 2 pi over delta t. Of course, this sampling frequency, this sampling time cannot be smaller than the time integration step of the Schrödinger equation. So you solve this time-dependent Schrödinger equation at small steps in time that you call delta t, and the inverse of delta t gives you the maximum frequency. So this method has a number of good features. The response to all frequencies is calculated from a single time evolution via a fast Fourier transform, whereas in the previous method you would have to calculate the response at each individual frequency independently. Very important, the numerical complexity of this real-time method is the same as ground state methods. You don't have to calculate any unoccupied virtual orbital, and very important as well is that basically you calculate only the information that you need. You don't calculate huge operators, huge integral kernels just for the sake of solving matrix equations and throwing them away at the end of the day. This is suitable for linear as well as nonlinear response. However, linear response requires finite differences, and ideally the time step should be of the order of the inverse maximum frequency. You remember that the maximum frequency that is accessible to Fourier transform is 2 pi over the time step. So if you are interested to the response up to a frequency of, say, 10 volts, then ideally you would like to have a time step that is of the order of 2 pi over 10 volts. But if you do so, the time step that you obtain is so large in practice that the numerical solution of the time-dependent Schrödinger equation is unstable. In order to enforce stability of the solution of the time-dependent Schrödinger equation, you have to use time steps that are so small that in principle you may calculate frequencies that are much larger than strictly needed. So once again, you waste part of your computer resources just because of numerical stability. Let me make a break of 15 minutes. It is...
Stefano,
sì?
If I may comment, Jennifer mentioned that at 10:30 they have set up the group picture to be taken outside.
Very good, very good. We will 10:30 will be during the break, no matter how short we make it. So we reconvene. I would say at on that clock at 20 to 11 at 10:40. Okay. We take the picture at 10:30 wherever it is. Where is the?
Just